ආකාර හතරකට බෙදා දක්වයි. එක යට එක ලියන්න මෙන්න මෙහෙම. ඔය 1 2 3 4 5 6 ඇඳක් උඩද මේව එකක් උඩද මන් දන්නේ නැහැ. ඔහොම වැටිගෙන මොකද්ද ඔය කරන්න කියන්නකෝ. කොහොමද පාඩම් කරන්නේ? ඔව් බල්ලා ඉගෙන ගන්න.
ප්‍රශ්න දෙකම තියෙනවා. හැබැයි මෙන්න මේ කොටසට අයිති නෑ. ඒ කියන්නේ මොකද්ද? යාලා පළාත් පාලන සහ කෘෂි පළාත් සහ කෘෂි. හරි. පළාත් පාලන සහ කෘෂි. පමණක්. පළාත් පාලනත් හරි කෘෂිත් හරි. හැබැයි පමණක්.
මම අටෙන්ඩන්ස් මාක් කරනකම් විතරයි ඉන්නේ.
ඔය අටෙන්ඩන්ස් මාක් කරනවා විතරද ඉන්නේ පුතා? දැන් ඔයා කියනවා මට අහන්න දැන් අටෙන්ඩන්ස් මාක් කරනවා විතරලු ඒ ළමයා ඉන්නේ. දැන් බලන්න ඒ ළමයාගේ තත්ත්වය. දැන් ඒ ළමයා කියනවා අම්මත් එක්ක මං අටෙන්ඩන්ස් මාක් කරනවා විතරලු ඉන්නේ. ඒ වගේම ඔයාගේ විභාගයට MCQ එක කරනකොටත් මං ඒ විදිහටම සලකන්නම් right? MCQ වලින් මං ක්වෙස්චන් පේපර් හදන්නේ. මම අටෙන්ඩන්ස් මාක් කරනවා විතරලු ඒ ළමයා කියනවා ඉන්නේ. මටත් ඇහෙනවා. මට හිතන්නේ BANS බාලසූරිය කිව්වේ. මේ මෙතන pop up වුණා.
Because of the global pandemic, everything has been changed. The things we did physically move on to the virtual world. As per you seen in this video, this is the one of the major problems nowadays we are facing. Because everything is conducted through online virtual sessions. The problem with virtual meeting is that the host doesn't know whether the participant is focusing or not the meeting. Even if the participant is not focusing on the meeting, the host even doesn't know, he can't change the way he presents the meeting. Do you think there is an existing solution for this problem? Actually, there is no solution. Even if you take a look at the existing platforms, they are not address this problem.
When you think about existing products, as an example, Zoom, which is allowed to conferencing the video, or any LMS system, learning management system, like Blackboard, which is using University of Westminster or University of Sydney. All of these video conferencing tools or any platforms, they are actually allowed to get student information. But any of these informations are not sensible to calculate or predict the student concentration level. This is the issue that we are talking about. We are trying to figuring out, is there a way to do that, or is there an existing way to do that? We didn't find any way to do that, or any tool that is allowed to use that.
Due to the pandemic situation, all the physical meetings, lectures and sessions, seminars and all the physical gathering are asked to stop or make them online. So as a result of that, all the meetings, lectures are made online, and as a good practice to secure ourselves from physical contacts. But when it comes to these online platforms, the main problem that we lack is that the host doesn't know the exact mentality of the participants. That's one of the main problem that we see in the present or current video conferencing or online or e-learning platforms like Zoom, Meet, Teams and all, etc. So that the host feel like he's just delivering a lecture or doing a session just in front of the camera, and also the participants also feel bored because participants always like to be pumped when there are like interactive sessions in the middle of interactive sessions and brainstorming session in the middle of lecture and all. So that is something we lack in the online platforms. In a thesis by Islam on problems with distance learning platforms, he has mentioned clearly that emotions play a major role in the interaction between the host, between the lecturer and the student, or the host and the client. But that's what keep the things together. In the current system, don't see any solutions out there like that. Even though there are many solutions just to predict the mental health, those predictions are not that efficient, because the key features that they are taking to predict the concentration level or the mental health of a person is not very precise, because some have taken the position of the head to see someone is very focused on something he is doing. But some people can sleep keeping their heads straight, right? So it won't be a good solution for them as well. So, but we in this project we have taken the facial landmarks and positioned the behavior of eyes and our mouth to predict the concentration. In a solution given by some students in India in 2016, I guess, they have developed a model. They have developed a model to predict the drowsiness level of the student or of a person. By that, they are trying to calculate the concentration or the mental health of person. But in that project, just giving a ML model is not enough, right? So we as a team, we as I-Lec came up with an idea to give a fully fledged application with a very beautiful front-end experience and with the powerful back-end model to give a very precise output about the mental health of the crowd that a host of the meeting, host of the session or the lecturer addressing to. So that's the gap that we are trying to fill out in present solutions that we have for digital learning and online meetings and give out a good product.
We are giving white paper here with I-Lec as a solution for this. In here we are going to detect the concentration level of participants and we are going to give a live feedback for the moderator who is conducting the session. So let's deep dive into the solution.
Proposed solution is a web-based application which is divided into two sections, front-end and the back-end. Back-end has built using serverless framework and used AWS cloud platform to host the back-end. It is implemented as serverless computing module. Back-end is consists with four main functions in Lambda form in order to perform get live data, join meeting, generate meeting, and predict concentration level. All these functions are deployed in a AWS S3 bucket along with the trained machine learning module, which is used to predict the concentration level. An API gateway has been used to trigger the relevant functions. Once a function is triggered, there is a DynamoDB to save or retrieve the appropriate data. Frontend is built using React framework and hosted in Firebase. Both host and the participants are logging using single landing page, and there are separate paths to create and join to the meeting. Once a participant joins, his landmarks, which is captured from the front end using Face API, will send to backend to predict the concentration throughout the meeting. Prediction results of the participant can be viewed only by the host as a graph. At the same time, concentration level of the participant will be shown as a real-time indicator in the UI as well. Apart from that, our solution has used Jitsi open source library for video conferencing.
So now we are here with the product walkthrough of the I-Lec video conferencing platform. When a user enters the website, he is directed to the landing page, and the landing page has two buttons, a create meeting button and a join meeting button. From the create meeting button, host can create a meeting, and by the join meeting button, someone with a valid host meeting ID can join a meeting. Now let's create a meeting. In order to create a meeting, you have to give a name. I'll give my name and create. As soon as we click the create button, we will be directed to the meeting page, which is given for the host. Here we are given with several buttons and graphs. First of all, we have the concentration level graph, which represents the precise level of the concentration of the participants in the meeting, varies in real time according to the behavior of the participants in the meeting. And also we can mute our audio, mute and unmute our videos, and also we can toggle the views according to our wish. And also we can share the screen, we can end the meeting, and this is special button to view the report, which gives the real-time data of the concentration level of the meeting throughout the session. Since we don't have any participant at the moment, the concentration level is 0 and the graph is also null. And also the final button is for copy meeting ID, which is used to copy the meeting ID. Now since we don't have any participant at the moment, we'll add some participant. I'll copy the meeting ID and share with some of my friends so that they can join. Okay, now I have shared the meeting ID. Within a couple of seconds they'll be here. Okay, we have Kavindu and Ravindu here. Since they have just joined to the meeting, the algorithm is working to calibrate itself to gain the facial landmark, so that's the reason still the concentration level is 0. Once since they are fully concentrating on the session, the graph will go green. Okay, now since they are concentrating the session very well, we can see that the concentration level has gone to 100. So even we can see that in our report also. So here I think one of them has not concentrated during the session, that's why it has gone 50%, because we have 2 participants, but they have been concentrating in the last couple of seconds. So if they are drowsy, like if they are feeling bored, the concentration level will become 0. There we go. So they are now bored about the session since I didn't do anything interactive. So the concentration level has gone down, and that's the end of the product walkthrough session of the host part.
As my teammate said, this is how participant can join a meeting from our I-Lec page. This is how it shows when a participant joins to a meeting which is hosted by another host. All the buttons are as same as the which were in the host page.
So for the data science component, we are going to use k-nearest neighbor machine learning algorithm. So we are going to use Google Colab to implement the algorithm data science component. So first we are going to import the relevant packages and libraries we need to implement this data science component. Once we imported those libraries, we are going to define 4 functions, which are the feature extraction functions. Those are eye aspect ratio, mouth aspect ratio, circularity of the eye, and the mouth over eye aspect ratio. So once we wrote that function, we are going to write another function which is calibration. In that calibration function, we are getting a delip detector and delip predictor and the video path. In this function, what we are doing is we are going to get a video and we are going to capture the frames from that video, and for each frame we are going to check whether the landmarks is detected. So once the landmarks is detected, we are going to extract a certain portion from the landmarks, and we are going to use our defined functions to extract the features, which are the core 4 features. So once we get those features, what we are going to do is we are going to get the mean and the standard deviation of those features, and we are going to return it. So this is the delip detector that we got. From that we are going to save delip detector and the predictor. So that's the function. So after getting those functions, we are going to save those functions into a file called total with main info CSV. So after that we are going to divide those data set into 2 sections, which is training set and the testing set. So we are going to read the features that we saved, which is filed from a CSV file. So once we read those data, we are going to divide it into two sections, which is training set and the testing set. So after that, we are going to use the training data set to train the machine learning module. So we are going to write another function called average. In this function, what we are going to do is we are going to take three adjacent frames and the prediction result of those three frames, and we are going to check whether the average of these three frames are greater than 0.5. It is greater than 0.5, we are going to mention it as drowsy. If it is less than 0.5, we are going to mention it as alert. The reason why we are going to do this is, for example, if the participant is in alert state during 3 seconds, if he blink his eyes, he would be mentioned as drowsiness. So to prevent this, we are going to take 3 frames and get the average of it. So that's the main functionality of the average. So after that, we are going to run a loop 45 times, and in this loop we are going to check the best value for the KNN neighbor. We are going to store it in a list. So from that list we are going to pick the best neighbor. So in this case we got the 38 is the best value. So after that, we are going to define a function KNN model. This is the function that we are going to use in our backend. So we are going to define another function called KNN model. This is the function that we are going to use in our backend. So in this function, what we are going to do is we are going to get the landmarks and extract the features from the landmarks, and we are going to get the normalized value of these features, and we are going to predict it. So for predict it, we are going to load the machine learning module that we served previously. In the previous, what we did is we saved the best suited accurate model in a pickle serialized format. So in the KNN model function, we are going to open it, and we are going to assign it into a variable. So we are going to predict those results from that neighbor value. So if the result is 1, we are going to mention it as drowsy. If else, we are going to define it as alert. So we wrote another function called live. So in that function, what we are going to do is we are going to get a real world data from our team members. What we are going to do is we are going to feed the video and check whether the function is working correctly or not. So if you scroll down, you will see that the function is working. So you will see that the participant is in alert state. These are the future enhancements that we are planning to implement in the coming future. First, we are going to improve the module accuracy. Due to the time constraint that we had at the implementation, we didn't have the chance to improve the module accuracy. In the coming future, with more data, we are planning to improve the module accuracy. Next, we are going to add more features to predict the concentration level of the participants. Currently, I-Lec only uses the landmarks of the participants to predict the concentration level. To add on to this, we are planning to add hand gestures and the body positions of the participants to predict the concentration level. At the SRS implementation, we identified there's a clear research gap in this problem domain. Therefore, with the help of domain expertise and the lecturers, we are planning to publish a research paper.
I joined with demonstrating the report for the front end, as well as I joined to gather the data and train the tree models and accuracy testing, as well as for test the model with real world data. And I joined with creating an endpoint to get the data for the report as well.
First, I started with frameworks and mockups, as well as in student components in the UI part. Also, I joined in accuracy part in the model, and also in Jitsi integration.
I participated in wireframes and mockup designing. Then I integrated Jitsi with our system, and also I made the landing page. In backend, I participated in data gathering part, and also I helped to train the model.
I created the host page components in the front end, and cleared the data for the machine learning model, and I participated in the accuracy testing and adjusting the algorithm, and in the API endpoints I created the host meeting.
In front end, I participated in creating on report page and as well as the report bar component in host page. In data science component, I did data gathering as well as some adjusting to algorithm for get a better accuracy, and also in backend wrote an endpoint to connect the model with front end.
My contribution is mostly on front end to deploy a pre-processing model using Face API JS to extract the facial landmarks and send it back to our main prediction model in backend. And also I participated in data gathering and training the ML models and also testing the ML models with the real world data sets.